So here we're going to give the definition of the localization of a commutative ring. So the idea here is that we have a commutative ring. All of the rings here are going to be commutative. And we want to create inverses for as many elements in the ring as possible, multiplicative inverses. So the idea is that we may not be able to do it for the entire ring, but what we can do is we can pick a particular subset of the ring. It's a submonoid. It's a particular subset that we'll talk about in a second. And we want to make all of these into units. All of the elements in S we want to now become units. And that's what's going to be happening here. We're going to be mapping all the elements in this set S into the group of units. But before we get into the definition, let's just quickly review what we mean by this set that we're localizing about, this multiplicatively closed subset of A. So S is multiplicatively closed if it's closed under multiplication. And we also require that the identity, multiplicative identity, is contained in the set S. This is the set that we're localizing about. The localization consists of a ring homomorphism F from A to B. F will be referred to as the localization map. The localization itself is the ring B. And we need this to satisfy two conditions. The first one is semi-obvious for the reasons I just gave, in that we want all of the elements in S to become units. So we're mapping S into the group of units of this ring B. The second property is a universal property. What does that mean? That means that if we have any other ring homomorphism, which also maps S into the group of units of this ring C, for instance, then any of these maps, if we have any of these maps, they factor uniquely through F. Factor uniquely through F. So that means that if we have our ring homomorphism, we need it to satisfy that it maps S into the group of units, that's given, but we also need this universal property, and that is that if we have any other map which does the same thing as F, so if we have a ring homomorphism that sends S into the group of units of the ring here, then it needs to factor uniquely through F. So it's universal in the sense that any other ring homomorphism, we can write it uniquely as we can factor it through F using this unique ring homomorphism H. And that means that this diagram will commute. Okay, so in this case, when we have this map F, this ring homomorphism, we call B the localization of A with respect to S. And obviously the localization depends upon the set that we are localizing with respect to. And notice the wording the. So this localization, as you might have guessed, because we have a universal property and some uniqueness, this localization is in some way unique. And in the following sense, or what do I mean by that? I mean it in the following sense. So if we have two localizations about the same set S, multiplicatively closed subset, then we can find a unique ring homomorphism from the two localizations, B to B prime, and we have some commutativity here again. So let's write down what this is saying. So if we have, again, a localization F of B, then for any other ring homomorphism which sends S into the group of units, factors uniquely through F. But we also have another one, this F prime, B prime, meaning that, again, if we have any ring homomorphism that sends S into the group of units, so in some way you can think of it as creating, forcing S to become a group of units, then it factors uniquely, it factors uniquely through F. So what we're looking for here is a unique ring homomorphism from B to B prime. So we need to find some way to go from B over to the B prime. The key point here is the universal property of F, and that is that we have freedom to pick this G. Okay, so we can pick this ring homomorphism G from A to C, namely we can pick the C in particular. We only need it to satisfy that it sends S into the group of units. Well, what map does that? Well, this map does. So they both have the same domain, and F prime, since it's a localization, F prime most certainly sends the group of units into the multiplicative group of its codomain. And that's what we need G to satisfy. And in that case, the universal property of F gives us this unique group homomorphism from B to B prime. So in some way we're kind of collapsing this diagram. So if we draw the new diagram where we choose G to be F prime, what we have is this localization B and another localization F prime. This localization satisfies condition number 2, namely that it is a ring homomorphism which maps S into the group of units. And then we're told that there exists a unique ring homomorphism from the localization to the codomain of this map, which in our case, we've chosen our map to be F prime, whose codomain is B prime. So, since this is any map that satisfies, we know that it must factorize uniquely through F. And so what I've used here is the universal, well, we can just say we've used the fact that F is a localization. So this is by the fact that F is a localization. And furthermore, we can do the same thing for F prime. That is that F prime is a localization, and F is a map satisfying it sends S into the group of units. So therefore, there will exist another unique group homomorphism from B prime to B. We don't need that exactly here. So we just need to check that we have commutativity, and of course we do. That's given to us by the fact that F is a localization. So that is that F prime is equal to first doing F and then doing H. So our unique ring homomorphism is this ring homomorphism H.